Good morning, all. The previous discussed about wavelength division multiplexing and the components, basic components that are used for wavelength division multiplexing. They are optical couplers. They are used for splitting and combining the signals, basically N by N couplers and star couplers, etc. Then now we are going to discuss about the multi filters that are used in case of wavelength division multiplexing. I think all of you know about the filters. Filters is nothing but that they are used as a selective devices that for a selection. In case of frequency, based on the frequency filters, we can say that I think all of you familiar with that low pass filter, high pass filter, band pass filter, band stop filter, etc. They are used to select a particular frequency from the incoming signal, that it can separate a particular frequency of signal at the output of the filter. As in this case of filters, here also in wavelength division multiplexing, uh, we want to select a particular wavelength from different wavelength of the signal. That is, optical filters are used for wavelength division multiplexing or demultiplexing, as well as a filtering of certain wavelength. In this figure, you can see that we are applying a different signal having different wavelengths, lambda 1, lambda 2, lambda 3, lambda 4, etc. That is to the filter. And after the filtering operation, we get a particular signal here, the lambda 1. That is, this filter is used to filter a particular wavelength, that is lambda 1. Okay. Similarly, if you want a particular wavelength is filtered out from the signal that having different wavelengths or here in case of wavelength division multiplexing, I think you can see the figure that is multiplexer. There are so many signals that having different wavelengths, lambda 1, lambda 2, lambda 3, lambda 4, etc. If you are applying this signal into the multiplexer, that is multiplexer is nothing but that is combining that signal into a single fiber, a single channel. That is, all these signals are combined into a single channel. That is the output of the wavelength multiplexer. The output line is single, but in that output line, there should be a different wavelength components. So, whereas in the wavelength filter, from the multiple wavelength signal that are present on the single line, from that we want to separate a particular wavelength. That is, the wavelength filter is used. In the figure, you can see there's a static wavelength, this cross connector. This device routes the signals from an input port to an output port based on the wavelength. They are used for multiplexing and demultiplexing. Okay, in the filters, there is important filter is that is fiber grating filter here. I think all of you know about the grating, the topic grating that you were discussed in, you were studied, you were learned in the first year physics. I think a grating is an important element in wavelength division multiplexing system for combining and separating the individual wavelength. So basically, a grating is a periodic structure or the perturbation in a material. This variation in the material has a property of reflecting or transmitting light in a certain direction depending on the wavelength. This grating can be categorized as either transmitting or reflecting. So you can see in this figure that's the basic parameters. You can see the figure, basic parameters in the reflection grating. Uh, that is the signal that or an optical signal having the wavelength lambda 1 plus lambda 2, that is incident on a particular surface, that is the and uh, uh, due to that incident, incidenting at an angle theta I, that is this angle is with respect to the normal to that grating, and due to the reflection, the signal is reflected, and that is due to the grating, that is separated as a different wavelength, lambda 1 and lambda 2 at an angle theta t. You can see in the figure. Here theta I is the incident angle, and then of the light, and theta d is the refracted angle. The lambda is the period of the grating, the periodicity of the structural variation in the material. In a transmission grating consisting of a series of equally spaced slits, the spacing between two adjacent slits is called a pitch. pitch of the grating. Constructive interference at a wavelength lambda occurs in the imaging plane when the rays diffracted at an angle theta d, satisfying the grating equation given by, I think you have studied in the physics this grating equation, that is lambda sine theta I minus sine theta d equal to m lambda, where m is called the order of the grating. In general, only the first order diffraction condition, that is m equal to 1, is considered. A grating can separate individual wavelengths since the grating equation is satisfied at the different points in the imaging plane for the different wavelength. Okay, the fiber Bragg grating. So the device called a Bragg grating, that are used extensively for functions such as the dispersion compensation, stabilizing laser diodes, and add or drop multiplexing optical fibers. This add and drop multiplexing we will discuss in the next session in detail here. These devices, that's called a Bragg grating. Bragg grating are used extensively for the functions of such as the dispersion compensation and stabilizing laser diodes and other multiplexing the optical fiber system. So an environment to create that fiber Bragg grating as an optical fiber. This can be done by using two ultraviolet light that beams to set up a periodic interference pattern in a section of the core of the germanium of the silica fiber. Since this material is sensitive to ultraviolet light, that is germanium adopted silica material, this material is sensitive to the ultraviolet light. The interference pattern induces a permanent periodic variations in the core refractive index along the direction of the light propagation. So the index variation is illustrated in the figure. You can see that is in the figure. There is index variation from is illustrated in this figure, where N1 is the refractive index of the core fiber as usual, and N2 is the refractive index of the cladding, and L is the period of the grating. You can see in this figure N1 and N2, and in effective, all these things are mentioned here. So you can see a germanium doped fiber core here, and interference pattern is obtained, and ultra wavelength of the ultraviolet light, that is 244 nanometer, and if an incident optical wave at a lambda 0 encounters a periodic variation in a refractive index along the direction of propagation, lambda 0 will be reflected if the following condition is met, that is lambda 0 equal to n effective lambda. N effective or n effective is the average weighting of the two indices of the refraction, that is n1 and n2. When a specific wavelength lambda 0 meets this condition, that wavelength will get reflected and all other will pass through. So these fiber Bragg, this grating technique, fiber Bragg grating is used for the filtering. So we have to filter out a particular wavelength. And this figure in the previous section, basic parameters, you can see that lambda 1 and lambda 2 is combinedly the wavelength having the lambda, an incident ray having wavelength lambda 1, lambda 2 is incident on a surface or incident, and by the reflection grating we can separate out these signals with the different wavelengths. That's the basic things behind the filtering, optical filtering. That is, grating is an important technique. So the fiber Bragg grating is commonly used technique here. And fiber Bragg grating are available in a wide range of reflection bandwidths from 25 gigahertz and higher. Application of fiber Bragg grating that can be found in WDM systems and in dispersion compensation techniques. So in the fiber Bragg grating illustrated in the figure, the grating spacing is uniform along its length. It is also possible to have the spacing vary along the length of the fiber, which means that that a range of different frequencies will be reflected by the fiber Bragg grating. This is the base of what is known as shift grating. So the main advantages of the fiber Bragg gratings are they are low cost, low loss, that is around 0.3 dB, and ease of coupling with other fibers, and the polarization insensitivity and low temperature coefficient, simple package. All these are the main advantages of the fiber Bragg grating. Okay.